We wanted to take the time this morning of reacquainting ourselves with linear regression and how it plays out with measurement error. And like I said, you saw your first structural location model, and we wanted to instill in you respect for proper, careful modeling of measurement error with multiple indicators. And we think that a first step in doing that well is to employ factor analysis. So we're talking about two kinds of factor analysis here. The classic technique, this is the only technique that existed up until 1967, namely exploratory factor analysis, which is used, as it says here on the slide 48, to explore the dimensionality of measurement instruments, trying to find the smallest number of interpretable factors needed to explain correlations among variables. The variables here is a measurement instrument, a set of measurement indicators of underlying dimensions. And it's exploratory in the sense that it places no structure on the assumed linear relationship between observed variables or on the linear relationships between the observed variables and the factors, but only specifies the number of latent variables. So EFA has to do with the number of latent variables, whereas CFA adds, which is what was introduced by people in the 60s, particularly called Euroscope 67 psychometric article, my mentor, confirmatory factor analysis, where you also hypothesize a factor model with a little bit more detail, allowing restrictions on the parameters of the model. And we're going to take a close look at that. Restrictions being some factors influence some indicators, but not other indicators. Yeah, I know it's hard to fit all the activities in. From that point of view, we recommend upstairs bathroom, up the stairs and to the left. All right, so lots of applications of factor analysis, and certainly in psychology, CBCL, MMPI, being two types of measurement instruments, sociology, attitudes, achievement items in education, where it's often called item response theory, IRT, and in mental health, where you work with diagnostic criteria of mental diseases or symptom items underlying that. The factor analysis model, then, is a linear regression model. So now we're going to just build on our linear regression knowledge. And we're going to talk in terms of dependent variables, which we always call Y, except when we are inconsistent in our slides. They are dependent variables because they are influenced by factors. You know, your attitude that you have influences how you respond to an attitude survey. So we're going to look at factors here. You see now a lot of EDAs, not just one, but EDA 1 sitting here, EDA 2, EDA up to via EDA K up to EDA M for this variable Y1. So this is a single measurement instrument variable, single indicator, which is linearly regressed on several predictor variables, several exogenous variables, as we might call them. In this case, M factors. But you have the same quantities as we looked at. We have an intercept, which is called nu, and a regression slope, which is called lambda for loading in factor analysis. And we have epsilons out here, which are the residuals, which have, again, mean 0, uncorrelated with the right-hand side variables eta, and with a constant homoscedastic variance. So epsilon is the variable, and its variance is called theta. We'll see the notation a little bit later. So anyway, we have a linear regression for each of the different y variables. And in this case, there are p y variables. So in the MMPI, for instance, I think p is like 200 or something like that. So you have several, in the mother's alcohol study, the head circumference study, we only had 2 dependent variables, but here we have many, many more typically. So many variables and many factors, but we are always going to have the situation where m, number of factors, is considerably less than p, the number of variables. So one question you might have now, how can we do linear regression when the right-hand side variables, the predictors, the x's, as it were, are actually etas, namely latent variable? How on earth can you estimate these lambdas of primary interest, these factor loading regression coefficients, regression slopes? And you do that through the magic of multivariate analysis. Through the fact that you have more information than just a single dependent variable, you have p dependent variables influenced by the same set of predictor variables, eta. It is possible then, under certain circumstances at least, to identify and therefore estimate these factor loadings. Now, we have the nomenclature here, which we just mentioned on slide 51. And on slide 52, we have written this in matrix form because we want to familiarize you with what you might see in the literature. Instead of listing all of those py's, you write it in bold form, which stands for a vector, which is just a column of y values. And u is a vector of intercept. And lambda is the matrix that we just looked at. Lambda is here. The lambda sit here. So you have columns and you have rows. I'm putting all of those lambda into one table. You are looking at your first matrix, a lambda matrix, which is having p rows and m columns. And then the factor vector and the residual vector. And then again, as we saw before the break, psi is the matrix of factor variances covariances, and theta is the matrix of residual variances covariances. That's a notation we're going to use throughout. And you have then a population covariance matrix for the observed variables y, which we call sigma, cap sigma, and you have this common form sigma equals lambda psi lambda prime plus theta. Let's see. Factor analysis terminology. Lambda is also given the term factor pattern in the psychometric literature, which is different than factor structure. Factor structure is lambda times psi, which, if you look at the formulas, actually then describe the correlations or covariances between the items, the factor indicators, and the factors. So it could be useful sometimes to look at the factor structure values to see how the items correlate with the factors, because then you can further interpret the factors through that and get an understanding for which items are particularly strongly correlated with the factors. Typically, however, the factors are interpreted based on the factor pattern, the lambda matrix. Haywood case we hear about now and then. That means that the thetas, the diagonal theta, jj, theta being the variances of these residuals epsilons, come out negative. Negative residual variances. We know that variances should never be negative, so that's a problem. And it happens in factor analysis at times, particularly when you have small samples and you try to extract more factors than maybe you should. So that's a signal that something is not going quite well. We have the term factor scores, which is an activity that you engage in after you estimated the model parameters, after you've estimated your lambdas, for instance. and done your interpretation, you may want to know each person's value on each factor. So you have a subscript I for individual I, and the little hat meaning estimated. So estimating factor scores is an activity in the factor analysis realm. Factor determinacy is a concept that measures the quality of the factor scores, actually giving the correlation between the true score eta and the person's estimated score. And that idea will come back tomorrow when we talk about dichotomous items, IRT, item response theory, and so-called information functions. We're going to tie the two concepts together. This is just a brief overview of the terminology. Let's see. Let me do 54 over here. So on the left screen, you have a model diagram for a two-factor model where the first three variables measure factor 1 and the last three measure factor 2. So we use terms like measure, y1 measures f1, or y1 loads on f1. In any case, the arrows go from f1 to y1. Thinking in terms of influence, F1, if you have a high F1 score, math ability, you're going to score high on Y1. But it's a linear regression. There you have the little epsilon sitting there, which has the variance data. Here sits the lambda. Usually you're not interested that much in the news, the intercepts, but only in the regression coefficients. Although this afternoon we're going to take an interest in news when we do multiple group analysis. So you have the definition of concepts here on the slide 54. Slide 55, this example is written out in detail in equation form, which in matrix form, you know, would be y equals nu plus lambda f. We use the term f here instead of eta. F and eta will be used interchangeably. When we talk about statistical methods, we're going to tend to talk about eta, because that's the standard SEM notation. But when we talk about examples, we tend to use F for factor instead, to bring it down to earth a little bit. So if you look at Y1, for instance, it's influenced by F1 with slope lambda 11. Lambda 11 sits out there to the left in the top left path, slide 54. However, the lambda for F2 is 0. So F2 has a 0 path. There's a 0 path from F2 to Y1. So you don't see the zeros, but you feel them, right? And actually, that's where the action is where the left out stuff in the model diagram is where the model content is, so it's a little funny. So you have zeros for the first three y's for F2 and zeros for the last three y's for F1. And you can then also derive the elements of the population covariance matrix, you know, a covariance matrix in a very, very large sample. We're just going to remind you of three things, okay, which will keep you in good stead for a lot of different applications. What's the variance of Y1? Well, in line with Linda's regression formulas, it's the square of the regression slope times the variance of the x variable, which in this case is F1. And variances of factors are given the name psi, PSI. So lambda squared psi plus the residual variance theta, which means that you could easily create the R squared, which is the same thing as reliability, by taking the first term divided by both of them, right? What is the covariance between two y's measuring the same factor? Well, it's the product of their two loadings times the factor variance. So the covariance increases as a function of the factor variance, psi 11 in this case. So if you have very little variation in this factor, you will have little covariance between the y's, irrespective of the size of their lambdas. What's the covariance between two indicators of the different factors, y1 and y4? Well, that's lambda, the product of the lambdas, times the factor covariance. Psi 21 is the covariance between the two factors. So psi 21 sits out on slide 54, out on the double-headed arrow between F1 and F2. That's psi 21 sitting there if you want to scribble here. This is sort of a fill-in exercise here. But that was a pedagogical trick in the 60s, I think, that fell by the wayside. So you have these, so in the covariance, the variances of the factors don't play in. The variance of the factor only plays in when you have items on the same factor. All right, so now you know a lot. You also may want to note that the model drawn on the left here is actually a confirmatory factor analysis model, as we will point out in a second. But you may want to note that now. So let's so here are two important slides to remember. There's a big history of arguing between EFA camps and CFA camps. EFA was the only technique available for a long time, as we said. CFA came around 1967. CFA then became the measurement model part of structural equation modeling. And many structural equation modelers and confirmatory factor analysts have less regard for EFA kinds of activities. Our feeling is that we should not ask if we should use EFA or CFA. What we really should do is use EFA and CFA together in an intelligent fashion. We'll tell you how. Very often also is the issue in factor analysis whether or not hypothesized dimensions can be found. And very often we see examples where people say, well, the theory says there should be 5 dimensions, like 5 dimensions of personality. Why does the factor analysis that I do not indicate 5 dimensions? Well, there's a big step between the hypothesized dimensions and the actual analysis. The biggest step being the measurements. And you can have measurements that are quite reliable, test-retest wise, but may not be that valid, may not be perceived by the respondent the way you have intended it. And it's that's the missing link that sinks many of these activities. The theory may be good, but you really have to spend a lot of time on measurement development. And factor analysis can help you do that. Factor analysis can tell you a little bit about how the respondent perceives your measurements, which may be slightly different than how you intended them to be perceived. So we lay out here a possible research strategy, a very stringent one perhaps, for instrument development, starting with a measurement theory and ending up with a well-developed measurement instrument. And we lay out 5 steps here. And the problem that we often see is that individuals tend to go right away to step 4 and become very disappointed when they find out that all the standard fit indices suggest that their models don't fit well at all. And then they backtrack. So we think it's much better if you can start with one, a relatively small pilot study, small n being the sample size, and use exploratory factor analysis. And as Linda will show you in a series of examples, revise items, perhaps delete items, perhaps add items to capture the hypothesized dimensions. Then you go to pilot study 2, still a small n, and you may want to formulate a tentative confirmatory model. And in pilot study 3, you take a little larger n and do a CFA based on the tentative one. Then you may even have a large enough sample to split it in half, random half of the sample that tests this model. But since you have a larger n, you also have a possibility of rejecting at least certain parts of the model. So you may want to further revise it and cross-validate it then using the other half of the data. So you have fresh data to test the model so that your p-values, probability that the model is one that have generated the data, those p-values are dependable. Only then are you really in a position to do a large-scale study where you can hypothesize confirmatory structures. And then you may want to move on to the topic we're going to spend time on this afternoon, namely investigate how the measurement instrument functions in other populations. So, let's talk about exploratory factor analysis then. And then it's time for Linda. It looks way too applied for me.
It's on. Okay. So now we're going to look at how we would carry out an exploratory factor analysis. And as Bengt has already mentioned, we use EFA to explore the dimensionality of a measurement instrument by finding the smallest number of interpretable factors needed to explain the correlations among the observed variables. And it's exploratory, as Bengt says, in the sense that it doesn't place any structure on the linear relationships between the factor and the observed variables, or the factor indicators, as we sometimes call them. The only specification you give in an EFA is the number of factors that you want the model for. So this is all about the number of factors. We use EFA to find the number of factors and also to determine the quality of the measurement instrument. And this is how it's very, very important. We can identify variables that are poor factor indicators and identify factors that are poorly measured, that may just not have enough factor indicators to warrant using them in a subsequent analysis. The data we're going to look at are the Halsinger-Swineford data. It's from 1939. And we're looking, wait, let me just do this. We're going to be looking at 4 domains: spatial ability, verbal, speed, and memory. We have a very small sample, 145 students. And it'll be interesting to note that this data was very, very well developed and very well collected, such that a 145 sample size is way sufficient for the analysis, and we'll be talking about sample size, which is everybody's pet question. But it shows that the reliability and the validity of the data say a lot about how many observations you need. You know, there aren't rules of thumb that really work if you don't take into account how well your data is measured and how well it measures what you intend it to measure. And I think this is the biggest problem. I don't think there's enough education out there about measurement. I don't know. I just get the sense that people don't spend time developing a measurement such that you really get your hands dirty with finding out about validity and reliability. We have a lot about reliability, but if you're reliably measuring something that you don't intend to measure, it really doesn't help you. So we're going to talk a lot about things like that today. I mean, I guess one of our goals is to try to raise the level of research. And we hope people like you who come to these courses, we hope that somehow we give you something that's going to make you do better research out there. So we have our sets of tests. Let me put the spatial ones on the right screen. So we have spatial tests, and there's the visual perception test, cubes, paper from board, lozenges. Verbal tests, a lot of verbal information, general, paragraph comprehension, sentence completion, things like that. And then the speed tests have to do with adding quickly, coding things, counting quickly, and telling whether things are straight or curved, but speed is of the essence here. And then memory, we have word recognition, number, figure, object number, relationships, number, figure relationships, and figure word. So these are the items that we're going to be doing an EFA on. Now, the next few slides, since this is the first time we've taught this class exactly like it is, with much, much more information that we used to put. So we think we might be running slightly behind. So I'm not going to go over these next slides. What they are is they're just giving you a feeling for what these items were like. So you can get a feeling when we start looking at them later, why the cross-loadings that we see in the EFA may occur. So we're just going to skip these for now, but we could come back to them. The two slides after them are the sample correlation matrix. And the point I want to make here is that it goes on for 2 slides. And the object of the exploratory factor analysis is to find in those correlations how they hang together such that you can determine the factors. Well, you can't look at that many correlations and do that yourself. And that's why we have statistics, to give us methods that can help us summarize and make sense out of data. And that's what EFA can do for us with this correlation matrix. Okay, and just some background now. In EFA, we analyze a correlation matrix. And that's not to say that we couldn't analyze a covariance matrix, but traditionally, that's how it started. And that continues today. We have a couple of estimators available, ULS, unweighted least squares, and it minimizes the residuals, the observed minus estimated correlations. So we have our sample correlation matrix that we just looked at. And when we do an EFA model, we can estimate those correlations from that model. And it's the difference between the model estimated and the sample correlations, each element of that matrix, and the average of that is what ULS tries to minimize. It's a very fast estimator, but it's not fully efficient. Maximum likelihood is computationally more demanding, but it is efficient. And it minimizes the difference not between the correlation matrices, but between matrix summaries, what's called the determinant and the trace of observed and estimated correlations. We used to recommend that people start out with ULS because it was so fast if you had a lot of items, but with all the power in the computers these days, you really don't have to, it's really not a concern at this point in time. Whoops. I just want to see what the next slide is. Okay, so let me take this one over here. And I know a lot of you have probably heard quite a lot of people criticize EFA. And like Bengt and I said, we've talked to people actually who have criticized it, and we've asked them, what is it you don't like? And I think it's boiled down to, it's not that they don't like it as a method, they don't like how it's used, how people use it. So that's what we're interested in, trying to use it better. Okay, so how does EFA work actually? So, and what is an identified model? So a model that's identified has only one set of parameter values. And in all those equations that Bengt showed you, y1 through y whatever, and all the etas, we could not estimate every one of the parameters there. We have to place some restrictions on that model in order for it to be identified. And there's an infinite number of ways those restrictions could be placed. So we'll talk about how it's done in practice. But the number of restrictions, first of all, that you need to place are m squared, where m is the number of factors. So if you have 10 factors, you have to place 100 restrictions. So m times m plus 1 divided by 2 restrictions come from fixing the factor variances to 1 and the factor covariances to 0. The remaining restrictions come about by fixing functions of factor loadings to 0 or factor loadings to 0. And ULS makes lambda prime lambda diagonal, so it fixes all the off-diagonal parameters at 0. ML does it differently. It's lambda prime theta inverse lambda is made diagonal. But the general approach is just to fill the upper right-hand part of lambda with zeros, lambda being the factor loading matrix. So lambda being the regression coefficients, really, in the regression of the factor indicators on the factors. So first of all, we have to make the restriction. We get a matrix that has those restrictions on it, and then we rotate it to interpretable factors. So we have two types of rotations, orthogonal where the factors are uncorrelated, and oblique, where the factors are allowed to be correlated. First, the orthogonal rotation is done such that the number of factor loadings close to 1 and 0 is maximized. So it's rotated until you have the maximum number of factor loadings close to 0 and 1. So it's sort of like in regression, you fit the line until the difference between the estimated line and the observed values is as little as possible. You then, to get the oblique rotation, start with the orthogonal solution and allow the factors to correlate such that the factor loadings are as close to 0 and 1 as possible. So that's basically the idea behind EFA. Now we're happy to say, a lot of new features in version 5 to do with EFA. We had only 2 rotations before version 5, Varimax and Promax. But now we have several new rotations, including Quartomin and Geomin. And you can, anybody who doesn't have the newest user's guide, it's on the website, and you can print it or do whatever you want with it. And you see the rotation option to see a full description of all of these rotations. And the exciting thing is that we get standard errors now for the rotated loadings for the factor correlations. And I think we're one of the few programs that provides standard errors for EFA. And we've also added new estimators. I showed you ULS and ML, but now in version 5, we have MLR, which is a non-normality robust standard errors and chi-square test of model fit, which provides those. We also have modification indices as part of the new EFA for the residual correlations. And we've added maximum likelihood estimation for censored, categorical, and count variables. Before, we only had EFA for continuous and categorical, with the categorical using weighted least squares. So categorical estimator has been expanded to maximum likelihood, and we've added censored and count variables to the scale types that can be used for EFA. We've also added 3 other things. You can do complex EFA, where you adjust for non-independence of observations, and you can include stratification and weights also. And mixture EFA, where you can do factor mixture analysis with class-specific rotations, and 2-level EFA, with new rotations and standard errors, including unrestricted model for both the between and the within levels. So those are topics that we're not interested in. You might be interested in complex EFA if you have complex survey data, and that you might find of interest even if you're here for today. But anyway, those are the new features that we have in version 5. Oh, what's that? I'll stay over on this. I'm not going over there. I knew there was a reason. All right, so, oh, thank you. So how do you determine, so EFA is all about determining the number of factors, number 1, and then seeing how well the factor indicators behave. But how do we know when we run an EFA? It's easy to put it into Mplus and run it, but how do you decide once you have all of this results what you do with it? Well, there are 2 descriptive values you can look at, eigenvalues and residual variances, and then you can also look at tests of model fit. We have the RMSR, which is the average residuals for the correlation matrix, which I talked about earlier, recommended to be less than 0.05. So it's the observed correlation minus the model estimated correlation averaged up. We want that to be less than 0.05. We also have our chi-square test. And this tests that the model does not fit significantly worse than a model where the variables correlate freely, and we want to have p-values greater than 0.05. I wrote out here the H0 and H1 models just for people to remember, because sometimes this is a little confusing. So the factor model, the EFA model, is H0. And H1 is the unrestricted correlations model, the sample statistics, basically. So and chi-square, we want the p to be large, so greater than 0.05. If it's less than 0.05, we reject the H0 model. Now, RMSE-A is another fit measure we can look at. It's a function of chi-square, and I give the formula here so you can see that it's not different. It's just a function of chi-square. Chi-square is a test of exact fit, whereas RMSE-A is a test of close fit, not as sensitive as chi-square to large sample size. And so let's talk about then how we would actually do this. We would look at all the, first of all, the first bullet, carefully develop or use a carefully developed set of variables that measure specific domains. EFA is very sensitive to the variables that you use when you run the analysis. And if you just happen to pick up a data set somewhere and you think, oh, let me do an EFA on this 100 variables and see what pops out, that's not the proper way to use it. And I think that may be where some of its criticism comes from. You need to know your items. You need to know what they're supposed to measure. So you need to develop them to measure like 5 domains or whatever. Let's say you develop 50 items, 10 each measuring 5 different domains. And you believe that each one of them measures only one of those domains, or if it measures more than one, you know the other one that it measures. So you have a hypothesis going into EFA about what you expect to see. And it's when you don't see what you expect that it helps you understand your data better. So it's extremely important to have good variables. And then after we do that, we determine the number of factors based on all of the measures that I just described to you in the last couple of slides. And once we get our results, we want to interpret these results. We want to look at the loadings, the cross-loadings. Cross-loadings can be bad, and cross-loadings can be okay. So we're not saying you should never have a cross-loading. We're just saying that if you have a cross-loading, it should be interpretable according to theory. It should be understandable. It shouldn't be like, why in heaven's name did that item load on that factor? It should be, oh, that item loaded on that factor, and it was written this way, and that's most likely why, and I'm okay with that. You know, it shouldn't be a surprise. So the quality of the factor, we look at the number of variables that load on the factor. We look at the factor determinacy, which Bengt mentioned earlier, the correlation between the estimated factor score and the factor. Now, as a part of an EFA, you may find it necessary to eliminate variables that just aren't working well at all, or rewrite them in the framework that Bengt talked about, doing a small pilot study first. And then you may find a variable that you've only got 2 indicators left for, and you don't have a way of getting any new indicators. You know, it's too late and you can't study it. Well, you may have to just not use that factor. Or if you do use that factor, you have to understand that that factor is identified only in another model by borrowing from other parts of the model, which may affect other things in your model. So these are the types of things you should be thinking of when you're doing your EFA. Okay. Too fast or okay? Okay. Okay, so on the right screen is the Mplus input. And to specify the EFA is easy. You just have to say type equals EFA 1,8, which means I want all of the first number is the lower level of the factor solutions you want, and the second number is the upper level. So I'm asking for factor solutions for 1, 2, 3, 4, 5, 6, and 7, and 8 factor solutions. So I'm asking for 8 different analyses. And I'm asking for estimator equals ML. Since that's not the default, I'm going to ask for maximum likelihood. So the first thing we said is that we would look at descriptive statistics. And one of those was the scree plot. So we examined the eigenvalues. And this plot's available in Mplus. This comes from Mplus. And usually people look at the number that are greater than 1. So that's 1, 2, 3, 4. And then that one's, right there. So when you look at this plot, you say to yourself, well, what does this tell me? It might not tell you exactly which factor solution is best, but it might tell you a family that you could look at and think about. So here, I would probably look at 3, 4, and 5. And we know that theory and the data were developed to measure 4. But we might want to see, well, what does 3 look like and what does 5 look like? I mean, does either one of those help us understand better what's coming out? We may ultimately settle on 4, but we want to take a while to think about it. Then I said we'd also look at residual variances, and that's in the last column here. But first, let me describe this table so that we're all on the same page. So what I've done in this table is summarize all of those exploratory factor analyses, the 1 through 8 solutions. So the first column shows the number of factors, 1 through 8. Then I give the chi-square, RMSEA, and RMSR, the 3/5 statistics I said that we should look at. In the last column, I give the second descriptive measure, the residual variances, and we don't want them to be negative. So there were no negative residual variances up to the 5-factor solution, but the 6, 7, and 8-factor solutions didn't converge, so we don't know. But if we try to now look at the fit measures, knowing what we know, we want in chi-square for the p-value, which is the third number here. We have chi-square, degrees of freedom, and p-value. We want the p-value to be greater than 0.05. Well, it isn't for the first 3 factor solutions, but it is for number 4 and 5. So that would cause us to consider 4 or 5. We want RMSEA to be less than 0.05. We go down, and that doesn't happen until the 4-factor solution. And we want RMSR to be less than 0.05, and that doesn't happen until the 4-factor solution. So this is how we use the information that we get from these EFAs to determine the number of factors. So what I thought is, we want to then go and look at the results and examine the factor loadings, which we're going to be doing, and determine if the factors support the theory. So on the screen here is the 3-factor solution, and it's the PROMAX, which is an oblique solution, so we're going to have factor correlations. And let me see just one thing. Okay, so I have to. Let me put the second part of that on this screen. Okay. And this is the way that I did this when I did this analysis. I don't think there's any place that what I did is written down. And a lot of times you don't necessarily need to do what's written down, but do what makes sense to you and what you think would be a compelling argument to somebody. So this would be considered an extremely strict interpretation of an EFA. But I want to do that sort of to dramatize that you need to do this carefully and you need to be consistent about how you do it. So what I decided was that here are our items down here, visuals through straight here and word R over there, and our 3 factors, which we are going to refer to this one as spatial, memory, speed, and verbal. So spatial and memory seem to be loading on 1 factor. But when I looked at this, I decided I was going to bold or highlight a factor loading if it was at least 2 times larger than any of the other 2 factor loadings. Now that is just something I made up, but I wanted to make sure that I was eliminating too many cross loadings, not just highlighting everything. So what that resulted in, if you have to look at the next slide, are the highlighted items for the first column, which are on 2 slides. It ended up with the items being highlighted for spatial and memory. I also made the decision, and then speed, you see the highlighted items here, and then verbal. Then what I decided was that if that criteria were not met, if there was no factor loading that was twice as big as one of the other ones, that I was going to bold this item, those 2 items, object and straight in this situation, and think about them later. Because straight loads on both spatial and memory and speed. So I would want to understand that better. And then we have our factor correlations at the bottom of the screen there. So that's the 3-factor solution. I then went on to look at the 4-factor solution. Keeping in mind the same type of criterion. And what we found in the 4-factor solution, which is what we expect 4 factors, and most of the indices made us point to 4 factors, the eigenvalues and these fit indices. And sure enough, the items do load on the 4 factors as expected. And a couple of other items come out, coding and figure R, to not load definitively on any one factor. So this is the Promax rotated solution. Now just to show you, this is the oblique solution. So I think this should probably be clear. So this supports theory. This makes us say, yeah, the 4-factor solution is the right one. Let me just show you one thing before we go to the 5-factor solution, and that's the Varimax solution, which is the orthogonal solution. And the reason I'm showing you this is to make the point that, and you can look at this in your notes, that the solutions are the same. You know, you don't very often get totally different solutions, orthogonal, oblique. They're usually pretty much the same. So you don't have to be really concerned about that. I think in most situations, the factors are going to be correlated. But now let's go on to the 5-factor solution to see what happened to that. So in the 5-factor solution, you can see that we got our spatial factor in column 1. We got our verbal factor in column 3, memory in column 4, it's over on the second screen, and speed in column 5. But the second factor did not load according to our criterion on anything, or it did not have any factor indicators that met our criterion. So based on that, you know, we would settle on the 4-factor solution. Fit the data well, fits theory well. We have an issue we need to think about, and that's what about the items that didn't load on any one factor according to our criterion? So what we would do then is think about why that happened. But before we do that, I want to show you some results from version 5. Before version 5, when we taught this class, you know, we went on to something after this called EFA in a CFA framework. Because when you did EFA, you couldn't see which factor loadings were statistically significant because you didn't have standard errors. And so we would recommend people to do EFA in a CFA framework where they could specify an EFA model and then obtain the standard errors. But we now have the ability to see what's significant. And in this information, which has a second page to it, I'm sure, the underlined entries are the entries that are statistically significant. And basically, what we find is all of the factor loadings that we had bolded earlier turn out to be statistically significant. So that's nice. But now we can look at the cross loadings, and we see there's other things. For example, on spatial, the addition item is statistically significant. It's not large, but it's statistically significant. So then the issue is, would you want to include it or not? You know, a lot of times people want to know how large should a factor loading be to keep that indicator. And I don't think anybody really has a good answer to that. But here we know that it's not very large, but it's statistically significant. We also know with a large enough sample size, anything would be, but this isn't a large sample size, it's only 145. So that's something to ponder. If we look at one of our misbehaving items, code, for example, we find that the loading on the memory factor and the loading on the speed factor are both statistically significant. And on the speed factor, it's not necessarily small, whatever that is, but it's smaller than the other significant ones on that factor, but it's not as small as addition. So this, now with the new version 5, you don't have to go through that EFA and a CFA framework. You're going to have your standard errors, and you're going to have to consider not only the size of the factor loading, is it 2 times bigger, but the significance, and then whether it would be meaningful to keep it in the analysis. I decided, just because, well, first of all, we'll examine the cross-loadings and show you how you might do that, at least for one of them. I think one would be enough? Okay. So you have these cross-loadings. You settle on 4 factors. That feels really good. It looks strong. But you have to decide what to do about the factor indicators that had cross-loadings. So let's examine it. Let's look at the variable code. It's supposed to measure speed, but it loads on memory and speed. So what it requires is matching letters to a set of figures. So that figure is a Z, and that figure is a K, and that figure is an A. And you have to run through here real quickly and put the right letter down. So yeah, it should be measuring speed, but it makes sense it should be measuring memory too. You have to remember the things to put them down quickly. So you can see that, well, yeah, I can see the cross-loading. So that's how you examine these items. You go through them and think about it. And if it seems like the cross-loading's okay to you, then you could include that item. But if it seems really bizarre, like it measures, I don't know, speed and something totally unrelated to anything in the item, then you would, like reading comprehension, I don't know, maybe it could have a little bit of that, but I don't think much. I would be suspect for reading comprehension. But anyway, you go through and you think about it, and you make sense of it, and then you make a decision. Am I going to keep this, or am I not? This item. And part of the decision might be how many items you have left. And I've got several of those that you can look and read and think through and make your own judgments about. So I decided I'm going to get rid of all of those items. I am such a purist that I'm not having anything tainted in my study. So I deleted them. So now when you do something like that, you better hope you can recover your results. Because if everything changes when you delete those 4 items, something suspicious is happening. So when I deleted those 4 items, actually, I recovered quite well the 4 factors, very well. And I also, but what happened, and the model fit well, everything was perfect. But what happened is speed now only has 2 indicators, and we know by now that is not a pretty picture. So what do? So are we going to use some other cross-loading variables that were significant on speed to try to beef this up? Do we have a way of getting some more factor indicators for speed? Or are we just going to say speed, we're going to give up on speed? And once again, I gave up on speed because I decided I'm such a purist. This is why I'm a software developer and not a researcher. So basically, we got rid of speed. And I want you to think when you go through this exercise, this is an exercise and this is how you should go through it. You may not want to make my decisions, but I want you to see that sometimes you can make a dramatic decision. So luckily, again, let's see, I have to get up to 100 over here. I was able to reproduce the 3 factors. Everything fit very well, and everything looked great. And this is, I think, quite a testament to Halsinger and Swineford that with a sample size of 145, it must be incredibly reliable and obviously quite valid data. And I'm sure they really developed these instruments very, very carefully. So this is how I would go through an exploratory factor analysis. Now, that's just what I'm saying. There can be other ways. There's no written rules, but it should be something you can convince somebody of the validity of. So just to quickly go over practical issues, choice of variables. I already said that, so I'm not going to go over that again. Sample size. A large sample size gives you more stable correlations, and you don't get as many of those Haywood cases that Bengt talked about, which are negative residual variances, which mean the model is not admissible. Small sample size can avoid problems with chi-square sensitivity, and heterogeneity can be avoided. And size of factor loadings, there's no general rules. And as you saw, you can drop variables that poorly measure factors and drop factors that are poorly measured. So this is just a little summary of what we did. Now here's a page which I think I won't go over just briefly, but you can't necessarily extract as many factors out of a set of data as you want. There's a limitation. A has to be less than or equal to B, where A is the number of parameters that are estimated, and B is the number of sample statistics, correlations, variances, covariances in your data set. So A needs to be less than or equal to B, and I give an example below that which you can, I think, work through. The bottom line being, if you only have 5 variables, you have B, number of variances and covariances 15, you will only be able to extract 1 and 2 factor solutions, not 3. And this, I think, is my last slide. And I'll once again go over this rather quickly. People always ask about sample size. And it's a good question because you're out there collecting data and it's expensive, and you don't want to collect too little because then you don't have the power to even test your hypotheses, but you don't want to collect too much because it costs a lot of money to collect data. So there's 2 things to think about. The stability of your sample correlations, or the data that you're going to be using to estimate your model. And in this first, to have a sample correlation of 0.5, or to have a correlation of 0.5 with a standard deviation of 0.1, you only need 56 observations, and you can go through the formula, which isn't very many. But what about stability of parameter estimates? That's really important, maybe more important. You know that you have to have a sample size larger than the number of parameters. But and if you have 5 dimensions, 5 items per dimension, if you go through the formulas 2 slides back, you'll find out that that model has 140 free parameters. So that would mean you would need a sample size of at least 140. And if you went by a rule of thumb of 10 per parameter, that would be 1,400. So you would need either 140 to 1,400 observations to have 1 through 10 observations per parameter. And that doesn't really tell you much. So what we always recommend to people is that you do a Monte Carlo simulation study. Very easy to do in Mplus. You do a simulation study using the parameter values in your data as population parameter values, and you find out how many observations do you need to be able to have the power to detect what you're looking for in that study or to reproduce your parameter estimates. And the paper at the bottom shows how to do that. And just an aside for people who don't know, on the Mplus CD that you get, when you install Mplus, if you do it as the default installation, you get the input and data for all the examples in the user's guide, and you get the Monte Carlo counterpart for the examples that created the data. So if you, for example, want to do a Monte Carlo study and you find an example in the user's guide that's like your study, well, you can use that Monte Carlo counterpart as a starting point. So a little bit on sample size. It's never satisfactory, but. And then we have further readings on EFA, and you have no minutes to start CFA. Or do we want to do a little start? Okay, and have a little shorter lunch maybe.
Well, it's only 10 to 12. Don't we go into 12:30?
No, 12 to 1:30 is lunch. Oh, yeah. Well, let me just think. 1:30, 2:30. No, it has to be 12 to 1:30 because we can only go to 5. So do you want to do a 5-minute introduction? Okay.
So we're heading for a lunch break at shortly after 12 here, where Mark, our videotaper, will break the stream, and we'll come back at 12:30. Sorry, 1:30. A little bit of a short lunch. And then the videoing will start up at 1:30. Technical information there. So that was a lot of useful information. Cross-loadings implies that an item loads on more than one factor, that is, measures more than one factor. Sometimes that's in line with your theory and it's desirable, and you can allow that. Sometimes it's against your theory, it doesn't make sense, in which case you may want to delete that item. The rotational schemes that Linda described can capture these cross-loadings, and you can reason about them substantively, as Linda showed in these pages. Linda talked about the technical underpinnings for rotations, the mathematically convenient step, fixing some parameters, and then the rotation to make the solution substantively palatable. None of that is what you do. I mean, that's all behind the scenes. But we want to give you a little bit about what happens behind the scenes, so you know. It could be useful when you do more advanced modeling. Anyway, so I'll talk about confirmatory factor analysis, introduce that a little bit at least. And we agreed that CFA goes beyond EFA by having more restrictions on the model. EFA has m squared restrictions, m being the number of factors. You don't work with those restrictions. They're taken care of by the rotational schemes. But in CFA, you're in charge of placing the restrictions. So you have to have in CFA at least m squared restrictions. And when you have more than m squared restrictions, you will then have a true CFA model. And those restrictions are on factor loading parameters, variances, covariances, and residual variances. Typical example would be that you hypothesize that a math test performance is, or performance on some math subtest is influenced only by a math ability, but not by the verbal ability that's measured by some verbal items. So you have these zero loadings that we talked about. We showed a picture, diagram. where we said the action was in the absent paths from F2 to the first 3 y's and from F1 to the last 3 y's. Those kinds of zero-factor loading restrictions is the hallmark of CFA. Typically, CFA then is interested in, after you've done a preliminary study like we showed, the several steps, you're interested in taking a new sample from the same population that you've been doing the exploration on to see if this hypothesized factor model fits the data, sort of a confirmatory aspect. You may also want to see if factor model fits a sample from a different population to see if you have measurement invariance across several populations. And we're going to take a look at the parameters of a confirmatory factor analysis, where factor variances show the heterogeneity in the population and factor correlation show the strength of association between the factors. So that's studying the properties of individuals in the sample that you're working with. Typically, we one interesting application, I should say, is the study behavior of a new measurement items embedded in a previously studied measurement instrument. So you expand your measurement instrument. In the CFA, you might still be interested in estimating factor scores, and it may be used to investigate a previous EFA more fully. So just a couple of application areas. Here's the model I talked about. It's a CFA. How many restrictions do you have? Well, you have 3 absent arrows from F2 to Y1 to Y3, and 3 going absent from F1 to the last 3. So that's 6. So 6 is certainly greater than m squared here being 2 to the power of 2, namely 4. So this is clearly a CFA model. So let me put 110 on one slide here and 111 on the other. So we're going to make now a distinction between 2 sets of parameters that I started talking about. Measurement parameters and structural parameters. Measurement parameters on slide 110 describe the variables, and structural parameters describe the people. So measurement parameters are variable parameters. Structural parameters are people parameters. Measurement parameters are the describe how the latent variables are measured by the observed variables. So that has to do with the factor analysis model intercepts, factor loadings, and residual variances. In the terms we used before, that's the nus, the lambdas, and the thetas. Structural parameters describe characteristics of the population, as we said. Has to do with factor means, factor variances, and factor covariances or correlations. Slide 111. And I would say that we're going to start off with talking only about factor variances and covariances. And then as the day goes on, we're going to bring in the factor means. Factor means are standardized to 0 always in the EFA context. We're not interested in any model structure for the means, only a model structure for the covariances and correlations. Since we work with latent variables, we have to find a meaningful metric for them, a scale. And the scales can be determined either by fixing the factor variance to 1, standardizing the variance. So in addition to fixing the factor mean to 0, fixing the factor variance to 1. That's what we do. That's the bottom bullet. That's what we do in EFA. But we could also fix one factor loading to 1 to set the metric of the latent variable. What that implies then is that, just like in regression, the regression slope for that item, that indicator loading on that factor is 1, saying that as the factor increases 1 unit, that item, that observed y, increases 1 unit. So we're setting the factor metric into the at the metric of y with fixed factor loading 1. So, and we're going to employ both of these alternatives in various settings. Necessary conditions for identification. We have to have fewer parameters, or at least not more parameters, in our hypothesized model, this is our CFA model, that's the H sub 0 model, has to be no larger than the number of variance covariances in H1, which is the number of sample statistics that you analyze, or more to the point, the number of parameters in the totally unrestricted model, the saturated model, the just identified model that has 0 residuals. This afternoon, later, we're going to talk about identification a little bit more in detail for one example, but essentially you should be able to solve for a parameter in terms of the variances and covariances to say that a model is identified. We're going to work with a set of rules of thumb instead to judge if a model is identified. A very practical way to check. You don't have to know anything if you don't feel like it. General statement. The program will complain if a parameter is most likely not identified, and that's a blessing of the maximum likelihood estimator, because it cannot compute standard errors if the model is not identified. You get a so-called singular information matrix, and you don't want that. And the program will tell you and point to the parameter that's most likely not identified. So you would have to add some restriction, perhaps fix that parameter at some value. Another way to check if a parameter is identified is if a fixed or constrained parameter has a modification index of 0, it wouldn't be identified if it's free. Modification index, we're going to talk about that in applications, is essentially what statisticians call Lagrangian multipliers, which is their way of complicating matters. It's just a way of checking that if you free that fixed parameter, will your model fit the data better? And it's in the chi-square metric of model fit, so it's quite useful. But the rules of, if you don't want to be totally lazy and let the program tell, there is actually rules of thumb. One factor model with 3 indicators is identified. 2 indicators, 1 factor, 2 indicators is not identified. But a model with 2 correlated factors, each with 2 indicators, at least 2 indicators, is identified. So based on only those 2 rules, if you look at that in the context of a bigger model, you can figure out if the model is identified or not. That alone carries you pretty far. We're going to talk about maximum likelihood estimation here to a large extent in CFA. CFA analyzes a sample covariance matrix. As Linda said, the EFA could also analyze a sample covariance matrix. It's actually the natural thing to analyze based on a normality assumption. But for EFA, it is okay to analyze a correlation matrix. It is okay. You get the right results. For some models, it is not okay to analyze a correlation matrix. Certainly a model where you have an assumption that the variances are equal, that model could not be estimated based on a correlation matrix where you have no sample information. It's like, sample variance information. So we're going to focus on maximum likelihood, and Linda described that it is a good estimator that does a very thorough job of matching the observed and estimated covariance matrices, and that there is a robust ML alternative that's robust to non-normality of the outcomes. So you don't have to worry about non-normality. We see that a lot in the on SEMNet and the literature. People want to get the Mardia coefficient of for testing normality. You don't have to worry about that. Non-normality, as we will talk about today and tomorrow, is okay when you use a robust ML technique, or MLR in Mplus. Everything comes out fine. Parameter estimates, standard errors, and chi-square. Here's the same chi-square testing strategy that Linda described for the EFA. Same strategy carries over to CFA. And at that point, I think we'll take questions and prepare ourselves for lunch break.
Right. And
so
let's take how about questions only on EFA, because we haven't finished CFA, and that will shorten the questions, probably. Yes. No,
let's repeat the question first. So the question is, we can get standard errors for factor loadings at this point in Mplus version 5. But what was the last part of the question?
But she didn't see the standard errors.
Oh, you didn't see the standard errors? Yes.
They're implicit in this significance test in this table because we had to have the parameter estimate divided by the standard error to know that that was significant. So although we didn't show them, the fact that we show the significance from the new Quarterman rotated loadings, but you will see them in a full version 5 output.
So the output in version 5 gives you the estimated factor loadings in one table, and then the standard errors in another table, and then the ratios in the third table. Yes?
I wonder whether there's a difference between Promax rotation and Quarterman rotation.
Is there a difference between Promax and Quartermean? Yes. There are two different rotation schemes. The latest research says that Quartermean is better. If you take your time and go through these pages and compare the solutions, you will find that the loading pattern, factor loading matrices, are very similar. You get the same interpretation. But I believe that the factor correlations are a little bit higher in the Promax than in the Quartermean. If you do simulation studies, you will find that Quartermean works better than Promax. But there is a new kid on the block, Geomin, which simulations show work even better than Quartermean, particularly in cases where you have these cross loadings that Linda talked about. That is, an item having a large loading on more than one factor, more than one column. Geomin is a good rotation technique.
Very quick question. In the analysis statement on slide number 76, you say type equals EFA 1 to 8 or 1/8. And if I'm understanding that right, which I don't think I am, the scree plot actually shows out the 19 factors. And if you say 1 and 8, doesn't that restrict it to 8 factors, or will the scree, it'll actually run the program out to 1 and 10?
How does that work?
So the question is about the scree plot on slide 77. Although we asked for only 8 factors, the scree plot goes up to 19. So the scree plot is based on the sample correlation matrix. So it's independent of the model. So even if you add...
It'll do whatever.
Yeah, I mean, it's a good question because sometimes scree plots are based on the estimated correlations, not the observed. But we found that working with the observed correlations is useful. So you will get the full set here. Again, this plot, although this was done in Excel, I believe that this plot can come out of Mplus as well. Yes.
Can I run anything in Mplus if all I have is matrix, correlation matrix data, but not the raw data?
So the question is, can you run an EFA in Mplus based on the correlation matrix without raw data?
For continuous outcomes, you can't.
What if I have categorical variables and I have these categorical correlations? I can still plug it in and use it?
If you have categorical variables, then you need to use raw data. The correlation matrix, even if it's a tetrachoric correlation matrix, alone will not be sufficient. You would need a weight matrix to go with it. And we don't allow the reading of both. You could use ULS.
Yeah, so Linda's answer is that you want to have the raw data to get a weight matrix for categorical data to get the standard errors in the chi-square. But if you only want the parameter estimates, you can use the unweighted ULS estimator on that correlation matrix, so you get at least the parameter estimates.
But no fit measures or standard errors.
Is there a way to test whether a cross-loading between two indicators is due to correlated error?
Well, I don't know if you can, okay, do the question.
So the question is,
I never remember.
a cross-loading between for an item on two factors, can that be due to the need for correlated errors? And it certainly can. And you can explore that. And we will tell you after the break about a very exciting new development where you can actually do EFA together with correlated residuals. So that's a first in world history.
Which is going to be in version 5.1.
Version 5.1. So you can actually see, you can hypothesize that these items have a residual correlation and then see would they have a cross-loading in the EFA rotated sense. Yes.
On slide 73, is there a citation that you would recommend for discussing the difference between the types of forecasting and the there are still some
So the
So
question,
you want to repeat the question?
I think the question is, if you have to use CF or chi-square because your reviewer requires it, what do you do about the sensitivity of chi-square to large samples? And in the new things that we have, you'll be able to do what I'm going to say. You can't do it in EFA as it stands now. But basically, in a CFA model, what you could do is you could keep relaxing parameters in your model, freeing fixed parameters based on modification indices until you get a good chi-square. Then you compare that set of results to your other more simple model set of results and see if it changed any of the basic things, if any of the parameters in your original model are now significant or now not significant. But if that structure of the results in that original model hold, then you could say it was a sensitivity to the large sample.
Yes.
I still have a question about the script plot on page 77. I wonder what the variance is explained. Is the total variance of item or the common variance by each factor?
So the question is about variance explained related to eigenvalues?
Yeah.
Yeah, so there is a whole history of this, variance explained. It has to do with the traditional way of doing factor analysis by really doing principal component analysis. Principal component analysis it really has a different aim than factor analysis. Principal component analysis is geared at explaining variation. Principal component that explains a lot of variation in your data. Factor analysis is different. It explains correlations. It doesn't try to maximize any variance. Now, PCA, principal component analysis, can be seen as an estimator for the factor analysis model, but it is a biased estimator. And bias may not be bad, so it can still be a decent estimator, at least a starting value generator. But factor analysis really isn't geared towards explaining variation. So that's an old, I wouldn't say old wives' tale, but it isn't really what you should go after. Although, of course, it's interesting, just like Linda said about R-squared and model fit, to have a model where the factors explain a lot of variance in the items. So for instance, if you have an orthogonal solution, which means uncorrelated factors, you could look at a factor that is a column in the factor loading matrix, right, where the rows are the variables, and add up the squared loadings and see how big that sum is. And that is related to what we do in eigenvalue plots. This has to do with the variance explained in that sense, if you make that connection between PCA and factor analysis. So one could, as a descriptive measure, try to figure out how much variance a factor explains, but that shouldn't be the guiding light for choosing the model. First you choose a model, and then you see how much variance is explained, just like in the R-squared situation.
For each one, we just look at the pattern of the...
In this case, we just look at the pattern. The scree, here's the mountain, and here's the rubble that's falling down from the mountain. Here's the scree. You draw a line. What sticks up above the line is 1, 2, 3, 4. That's one way of doing it. Sometimes for other approaches, you look at those greater than 1. But this is a very rough descriptive way of doing it, which should then be combined with statistical testing and the substantive checking that Linda went through.
In terms of specifying to Mplus how to do some of these, like the different rotations and to get the standard errors, is that stuff in the user guide to figure out what instructions you add to the, to get Mplus to actually do it? Like when we're at home and trying to figure out how do I get standard errors, where do we get that syntax from?
So the question is, how do you get the syntax to get the rotation that you should get?
Well, oh, go ahead.
That's all you have to say.
No, but if you want more information, if you want more information about EFA, go to the chapter 4. It's all the EFA examples, and it's going to take you through different things. And then you're going to see the rotation option, and then you can look up the rotation option in the user's guide, and that's going to describe all the different rotations. And so I would start with the examples chapter where the first example is always totally described, and then I would go to the different options for a fuller description.
And there we also have references to excellent literature. For instance, Michael Brown, the renowned psychometrician, has written a 2001 article in MBR, Multivariate Behavior Research, on rotations. And he talks about direct quartermin, which is the default that you get out of this. But if you want another one, geomin, you say rotation equals geomin here. And he describes that one too and shows that it works well. Yes, lady in red.
In addition to the scree plot, can you also request Horn's parallel analysis or the minimum average partial?
So the question is about the scree plot and the so-called parallel analysis. And for those of you who don't know what that is, I believe it has to do with generating random data to see what the fluctuation in the eigenvalues are, and then seeing if you have any, if this increase here is significantly different from a pure rubble. That is not included in the Mplus at this point.
For the Vellister's minimum average partial,
Say that again, please.
minimum Vellister's minimum average partial.
That's not included either, no. If you have these urges to have more options like that included, send us an email and we put it on the wish list. And the more people ask for it, the higher it floats up towards the top of a very, very, very long list. Yes.
Okay.
I have two questions. One is the critical value of the RMSEA 0.05. Where does it come from? And the other question is, if you have illustrated the estimators of the OLS and of the ML, but if you read the standard books on the exploratory factor analysis, they normally go through 3 other estimators. I can't remember what they're called, but how come you choose to use the ULS and the ML rather than 4? I know that the ML is standard, but the ULS doesn't seem so standard, so I'm curious on why.
Do you want to repeat the question?
Yeah, so the question was about fit indices like RMSEA and cutoff points like 0.05, and the second question was about the estimator choices here, ULS and ML, and there are many other estimators in the literature.
Well, I can answer the first question.
Okay, that's fair.
The first question is the cutoffs come from a paper by Peter Bentler from many, many years ago, which should be cited in a dissertation on our website by a student with the last name YU, who studied similar cutoffs for categorical variables. So the numbers come from those 2 papers.
And it is a little bit arbitrary, you know. You can't have general rules like that work for every situation. So it's quite arbitrary. And even for the CFI, Comparative Fit Index by Bentler, sometimes it works really well. Sometimes it's much too lenient, just makes you happy. And then I think you should instead take Linda's approach of the, testing the sensitivity against other models and seeing if your core key parameters have changed. It's probably better activity.
And also look at a set of fit statistics. And if only one says the model fit, don't just say, oh, good, and then ignore the rest. Think about why the others are saying it doesn't fit.
And regarding estimators, I think the psychometric literature, the books on factor analysis are lagging behind a little bit. They certainly deal with ML and ULS, but they also have the classic earlier or now historic, I would say, estimated like principal factoring, iterated principal factoring with iterated communality estimation. I don't think we need all of that. I think we can cut off the history at ULS and ML.
Can you elaborate on why you think we shouldn't?
I think if you do a simulation study and compare them, I think ULS as a representative of a simple approach would be at least as good as the other simpler, older. And ML is, the king of estimators. So. I could contemplate doing GLS, adding that, but I don't think we need that.
We may need to. It looks like we may need to finish this.
Yep, we probably need to go for lunch.
Yeah.